Okay, so now we have this example that is, we call it Laplace integrals. Okay, we're going to realize why it is like this, or why it is called Laplace integrals. So now let's assume that we have a function which is f of x equal to the exponential function e raised to the power minus k times x, where this x is defined for to be larger than or equal to 0. With k, this k is going to be a positive number. Then this function that we have here, this exponential function, has a continuous derivative, of course, because it's exponential function, so it is continuous. There is continuous derivation of this function, okay, and is absolutely integrable on the interval from 0 to infinity, right? Okay, so these are like the conditions that we have mentioned before. Okay, for the Fourier cosine integral, so if we want to make expansion of our function based on Fourier cosine integral, means that we're going to see only cosine terms. So compute the coefficients, which is a omega. As we said before, it is 2 over pi from 0 to infinity. The function itself, okay, the function with the substitution of z instead of x, so it is going to be e raised to minus k z cosine omega z dz, right? Okay, so we can make this integration, or we can solve this integration easily, and we're going to end up with this right hand side, which is 2 over pi k over k squared plus omega squared. Okay, then we can assume, or we can say that for x larger than or equal to, take care here, we have equal to, right? So it is including 0 with us. So our function can be expanded, okay, based on cosine expansion only. So we can expand our function, or we can represent our function as cosine with cosine terms only using this. We can say f of x, which is equaling to e to minus kx, equals to 2k over pi, 2k over pi, the integration from 0 to infinity, 1 over k squared plus omega squared. This is the denominator here, times cosine omega x, right, d omega. So this is our Fourier integral, cosine Fourier integral, if we want to put it like this, because it is consisting of cosine only, and we are using omega. As we said, it is the integration variable instead of the summation index that we used before for the cosine series of, or Fourier cosine series. Okay, so now we have, this is for the cosine series. Let's go to exactly that we are going to the next step, which is we can compute sine coefficients. So our sine coefficients is going to be related to the coefficient BW, okay? It equals to 2 over pi, the integration from 0 to infinity, the function itself raised, which is e raised to the power minus kz times sine omega z dz, right? So this is sine here. This is sine in our case, right? Because this is the definition of b omega. So if you are going to make this integral, you are going to find that it gives us 2 over pi omega over k squared plus omega squared. Okay, so this is our integral. Okay, remember this is from 0 to infinity, not minus infinity, because maybe it will vanish or something if we are going to deal, or I mean that we are looking to the integration from 0 to infinity. Okay, but remember here this bw, as we said before, or the sine function, it doesn't, the function disappear when we are putting our independent parameter with 0. So we said that then for x larger than 0, larger only here, okay, there is no equal sign here. Okay, we also have this expansion based on the sine, or beta, or bw. It's going to be f of x equal to e raised to minus kx. It equals to 2 over pi from 0 to infinity, the integral omega over k squared plus omega squared, okay, times sine omega x. This is the sine expansion of the function. And the hint here, the small hint, is this integral is 0 for x equal to 0, right? If x equal to 0, you are going to find that this is going to vanish, right? And so does not represent f of x there, so we do not put equal here. Okay, and this is actually, we have said that before, if you remember. Here, do you remember? The cosine integral converts to f of 0 from the right at x equals 0, and the sine integral converts to what? 0 at x equal to 0. So we have mentioned this before in the previous video. Okay, so actually the meaning now for using this as we said the Laplace integrals, these integral representation are called Laplace integrals, because a omega is 2 over pi times the Laplace transform of sine kx. If you do not know what is the meaning of Laplace transform, please revisit my previous videos. Maybe I can put the link. It is already, I was explaining about Laplace transform in engineering mathematics 1 level 1. Okay, while bw is 2 over pi times the Laplace transform of cosine kx. So if you know sine and cosine kx Laplace transforms, you are going to understand it. But anyway, this is something additional. We are not concerned with it now. But anyway, our main concern is that we have represented our function with sine terms only, or we have represented our function with cosine terms only. Okay, so that's the meaning, or this is the main issue for us, that expansion or representation of the original function with sine or cosine terms. Okay, here we come to the end of this video, and see you in the next video.